So welcome back. As promised, we are going to do a little bit more applications of Bayes' theorem, and then we'll move on to some other probability-related stuff. So by the way, when you calculate the answer to the question that I gave you before, namely what is the probability that you flipped, that you picked the unfair coin, given that after flipping it 3 times, you actually have tail, 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 the answer that you should get as computed by one of your colleagues is 1/9. So it's not a half anymore, it's shrunk quite a bit. Which makes a lot of sense because tail comes up with probability 1/4 if you have picked the unfair coin, so getting it 3 times is a low probability event. So rationally, you should not be very convinced that you picked the unfair coin. If you did, you were sort of unlucky. Okay, so this is something that in fact we've already seen. This is the revised formulation of Bayes' theorem with the fully expanded formula for calculating the probability of event E. That's why I didn't show it to you before, because it looks scary, but in fact it's not scary. We've used it before without looking at it. And you know, in Italy people say, if your eyes don't see it, your heart is at peace, so it doesn't feel scared. Well, so we used it, we just didn't spell it out, so we felt at ease with it, so now we can spell it out. So this formula says, again, that if you want to compute the probability of E, what is it that you need to do? You compute the probability that E occurs when F occurs, and the probability that E occurs when F does not occur. And you sum them together. And you have the probability that E occurs in general. Because E can occur when F occurs or when F doesn't. And these are the 2 possibilities. So in fact, this looks scary, but intuitively, it's not scary at all. In our example before, this meant compute the probability that you get head, head, tail when you flip the unfair coin. Compute the probability that you get head, head, tail when you flip the fair coin. That was the other possibility. You sum them together, you get the probability that you got head, head, tail in general. So, and in case you're interested in the math, this is why that's true. And there are a couple of questions there, which I encourage you to answer at your leisure and ask me questions if you don't understand why this holds. So, use Bayes' theorem at work on a pretty classic example. Some people think it's a paradox, but in fact, it's not a paradox. It's just probability at work. There are 2 questions that have to do with families having 2 children. You know that a couple has 2 children, and the older is a boy. What is the probability that they have 2 boys? The version reloaded say, a couple has 2 children, one of which is a boy. What is the probability that they have 2 boys? Now, when they look at this, most people think it's the same. Well, is it? Let's see. One of your colleagues is just already getting bored. Okay, so this one is dead. Fortunately, I have called redundancy back up here. Okay, so let's look at question number 1. What was the setting? Okay, we had 2 events, E and F. The event F was couple has 2 boys. Event E was the eldest is a boy. So we want to compute the conditional probability that the couple has 2 boys, given that the eldest one is a boy. So to do so, we don't really need the full power of Bayes' theorem. So let's use the standard formula. Then later on, we'll do an example with Bayes' theorem. The standard formula says, okay, compute the probability of the intersection and divide it by the probability that the eldest is a boy. So what is the probability that the eldest child in a family of 2 is a boy? It's a half. Because the eldest one could be either a boy or a girl. So it's a half. So this makes sense because the event T corresponds to 2 possible outcomes, boy-boy and boy-girl, out of 4. Okay, so what is the probability of E intersection F? Okay, E is BB, F is BB, Brigitte Bardot, for those of my generation. For you, probably that doesn't say anything. But she was pretty popular at some point. Well, at some point is a long period of time, but it was prehistory for you. Okay, so what is the probability of E intersection F? It's just the probability that you get boy-boy. And what is the probability you get boy-boy? It's 1 over 4. So now we have everything. This is 1 over 4 divided by a half. So that's time 2. So it's a half. Which makes a lot of sense. Why? Because if somebody tells you the eldest of the 2 children is a boy, you know that there are only 2 possibilities, either boy-boy or boy-girl. The probability that you get boy-boy is 1 over 2. Okay, so the probability that a couple has 2 boys, if the eldest one is a boy, is a half. But now, what is the probability that the couple has 2 boys, given that now E is the event, one of them is a boy? And F, oh, sorry, it's not the probability, it's the event. One of them is a boy. I'm already thinking in terms of probabilities here, but that's the next step. And F is still the event, boy-boy. Okay, again, we can use the conditional probability formula, which is the same as before, but now we need to calculate, well, okay, sort of the probability of E. What is the probability of E now? Okay, the probability of one of them is a boy is, as one of your colleagues said, is 3 out of 4. Why? Because E is the event that consists of boy-girl, girl-boy, girl-boy, boy-boy. The only one that doesn't work is girl, girl. Two G. Okay, so again, the probability of E intersected F is what? Same as before, it's 1/4. Because the only combination which is both in F and E is boy-boy. So what is the probability that the couple has two boys, given that one of them is a boy? Well, it's sorry. It's the probability of the intersection, which is 1/4 times divided by 3/4. So it's 1/3. It's not a half, it's 1/3. And again, this makes a lot of sense. Why? Because if you look at the set of possible outcomes, when somebody tells you one of them is a boy, there are three possible outcomes, not two like we had before. And only one of them is good. Well, at least good in this setting. I'm not saying the boy-boy is necessarily good as a combination. It depends on the boys. But in this specific scenario, that's what the event we're interested in. So this probability is 1/3. So the two are not the same. And to solve this exercise, where we really didn't need, we could have used Bayes' theorem, but it was simpler to do it this way. Now let's look at an exercise where we are going to use Bayes' theorem. And this comes from a New York Times article by John Allen Paulus, who's a very, very good writer. He's a mathematician who specializes in explaining mathematics to the masses, to the point that he even has a column, or had a column, I don't know whether he still has it, in the New York Times. And in one of these columns, he was, of course, talking about Bayes' theorem. What is the setting? The setting is that you have three coins now. Two of them are fair, and one is counterfeit. The counterfeit coin is such that if you throw it, it always lands heads. Oh, it's a coin with two heads, essentially. Now, you pick a coin, you don't look at it, and you flip it 3 times. And it lands heads each time. Now, before you actually threw the coin 3 times, what is the probability that you would assign to the event, I flipped the counterfeit coin? Well, you had 3 possibilities. You pick one at random. The probability is 1/3. It's 1/3. But now you flipped it 3 times, and you get head, head, head. What is the probability that you should now rationally assign to the event, I picked the counterfeit coin? Well, the result is 4/5. Why? Well, Bayes' theorem. So it's not 1/3 anymore, it's nearly 1. It's 4/5. So what is it that we want to compute? We want to compute, again, a conditional probability of 2 events, where event F means counterfeit coin flipped, or picked, actually. And E is the event head, head, head. And since it's an event, let's make it a set. Now, how can we compute this probability? Well, this probability is what? Okay, sort of, we use Bayes' theorem in the less scary formulation. We say it's the probability that I get E, and above the fraction, I have the probability that I get F, and then the probability times the probability that I get E, given that I pick the counterfeit coin. So we now need to calculate these three different probabilities. Now, remember that P of F is our prior probability. What does this mean? This is the probability that I can assign to the fact that I picked the counterfeit coin when I picked it at random out of 3. That's 1/3. Sigh of relief. Okay, so what is the probability that I get head, head, head if I tell you you picked the counterfeit coin? It's 1. Why? Because the counterfeit coin always lands heads. I told you the probability of heads for the counterfeit coin is 1. So if you flip it 3 times, you get head the first time with probability 1, head the second time with probability 1, head the third time with probability 1. You multiply 1 together 3 times, you get 1. It's a certain event. If you flip a coin which has head on both sides, you get a head always, isn't it? Okay, now what is the probability of E? Okay, so let's write down the scary formula, which is not scary at all. This is the probability of F times the probability of E given F plus the probability that I don't pick the counterfeit coin, so I picked one of the 2 fair ones, times the probability that I get head, head, head when I pick a fair coin. So what is this? Well, the first part we already calculated the terms of. It's 1/3 is the probability of getting the counterfeit coin times 1, which is the probability of getting head, head, head if I pick a coin that only has heads. Plus, what is the probability that I don't pick the counterfeit coin? It's 2/3 because I have 2 coins, which are fair, times the probability that I get head, head, head if I'm tossing a coin which is fair, and it's 1/8. Okay, so what is this? It's 1/3, another sigh of relief. I hope it was relief, plus, well, sort of, so let me, instead of doing the summation, let me do something which will turn out, I think, be useful. So let's be lazy. Why should we calculate when we don't need to? So this is, I put the 1/3 outside. This is 1 plus 1/4. Yeah, because this becomes 1, and this becomes 4 if I divide both by 2. And I take the 1/3 on the outside. So this is 1/3 times 5/4. Now, this 5/4 will turn out to be handy later on, because remember, the answer we want to get is 4/5. That's what Paulus told us. Okay, now we have everything. We have everything. We can calculate. So the probability that I flipped the counterfeit coin, given that I observed head, 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 is equal to what? Okay, below the solid line, I write the probability of E, which is 1/3 times 5/4. Above the solid line, I write the product of the probability of F, which is 1/3, times the probability that I get head, 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 if I picked the counterfeit coin, which is 1. And now this thing and this thing disappear, so they cancel each other out. So what I get is 4 out of 5. Which is exactly what the New York Times article told us the probability should be. So again, it's natural that you would expect that the probability has increased, that you've actually picked the counterfeit coin if you saw head, head, head. Because the probability of head is 1 for that coin. If you had picked one of the fair coins, it would sort of be already unlikely that you get head, head, head. It's only 1 in 8, the probability. And in fact, you will see this probability go very, very fast, extremely close to 1. So for instance, if you flip the coin 5 times and you get head, 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 then you will see that the probability is very, very close to 1, even closer than 4 out of 5. And if you keep flipping again and you keep getting heads all the time, then you know, wow, that must be the counterfeit one. So far, so good. Again, the calculations are sort of immaterial. The important thing is the process. And the process is always use Bayes' theorem plus our checklist. Namely, find out what the events of interest are, calculate their probabilities, feed the result into Bayes' recipe, and out comes whatever food you like. Well, whatever number you like, or whatever number you get. So let me give you a real life, well, a more real life, sort of real life use of Bayes' theorem. Now, we're not going to do the calculations here. I encourage you to do them at home. And this is a very typical application of Bayes' theorem today, and it's got everything to do with tests for diseases. So suppose that there is a skin test for tuberculosis, which is luckily a very uncommon disease these days, but not so long ago, and still in many countries, it's not an uncommon disease. Now, the test is such that if you have tuberculosis, you test positive 98% of the times. And if you don't have tuberculosis, the test comes back negative 99% of the times. So there are both chances that there are false positives. This is the 2% here. You test positive, but you don't have TBC. Or false negatives. You actually do have it, but you test negative. That's 1%. Now, doctors have collected data that tells us that 2 in about 10,000 people have tuberculosis. Now, you go to the doctor, you get the test, and you're positive. How worried should you be? You know what? Surprisingly, you feel that you should be pretty worried, but in reality, the answer, when you do the calculation, is that you shouldn't be worried at all. The chance that you have TB is actually 0.0192. It's incredibly low. Use Bayes' theorem, and you will see that you should not be worried. The reason for this is that TB, according to this data, is a very rare disease. Only 2 out of 10,000 people have it. Now, I don't know how accurate this data is, but it's a very, very small fraction of the population that has it. Just to convince yourself of why this matters, redo afterwards the calculations, assuming that you live in a country where 2% of the people actually have TB. Then you should be worried. You will see that the chance that if you test positive, you actually have it is not 0.0192. It's substantially higher. So, you know, of course, we are always worried if we go and have a test and we test positive, but perhaps sometimes we shouldn't. And your doctors should actually use Bayesian technology to give you good advice. Of course, you will be testing more and more, and well, if you turn out to be positive according to a lot of tests, independent tests, then you should start getting worried. But anyway, here I think it's a pretty moot point because I don't think that TB actually exists here in Iceland, but perhaps it does. I have no idea. Okay? There was a time where people were vaccinated. I don't know whether it's still the case. But that's a different course. That's molecular biology, or we are not doing biomedical engineering here. Not yet, at least. So there you are. Today, this guy was Reverend Bayes, the guy who gave us Bayes' theorem. And what he gave us today plays an important role in computer science. You look for Bayesian uses, spam filtering, Bayesian networks, probabilistic inference, decision support systems, it's all there. And you know, you look at the formula, it's not complicated. It's a very simple one. We could even prove it ourselves in 2 minutes. It's just a minor variation on the formula for conditional probability. So if somebody tells you the stuff is to be difficult to be useful, laugh at them. Well, perhaps that's a bit rude. Don't laugh at them. Tell them, well, you know, it's not true. Look at Bayes' theorem, for instance. And you explain it to this person over a party, a glass of beer or a wine, and you will be friends forever. Perhaps. I don't know. Either the person runs away or will be very grateful that you have explained why this person should not be worried if she tests positive for tuberculosis. Okay, so any questions about Bayes' theorem? If not, let's go back in time. And now we are not going back to the time of Bayes, we are going back to the time of a guy called Bernoulli. Well, in fact, Bernoulli was one of a Bernoulli family, and they were all mathematicians, basically. So this was one of the Bernoullis. There is a typical, well, it's a fairly typical type of experiment in probability theory, which is called Bernoulli trial. And it's the performance of an experiment with only two outcomes. For instance, tossing a coin. Or the probability that or the successful or unsuccessful transmission of a packet of data in a communication protocol. You're either successful or you're not. Should I stay or should I go? To be or not to be? These are all examples of Bernoulli trials of sorts. Now, typically the two outcomes in a Bernoulli trial are called success and failure. The probability of success is usually denoted by P, and the probability of failure by Q, but Q must be 1 minus P anyway, because otherwise we don't have a probability distribution. Now, Bernoulli trials might be mutually independent. What does this mean? Well, think about tossing of a coin. The coin doesn't remember what it did when you tossed it 1 million times before. If you toss it again, the probability that it lands up heads is always the same. It's independent of the fact of all the tosses that you had before. It's not a coin with memory. Okay, so if it's a fair coin, the probability that you get a head will always be a half, no matter how many times you toss the coin before. That's an example of Bernoulli trial, which is mutually independent. Every time is like starting from the first time. It's like the first kiss, whatever. Okay, so let me ask you, is casting a die a Bernoulli trial? Some people are shaking their heads there. Why is it not a Bernoulli trial? Because it has 6 outcomes, not 2. Not 2, absolutely. Okay, so Goodwin is saying, doesn't it matter what you're looking for? I could turn this into a Bernoulli trial if I said, I'm interested in the events, say, even, odd. Then it becomes a Bernoulli trial. But if you're interested in all the possible outcomes, then it isn't. Absolutely. Let's qualify our answers. But in general, it isn't, because you're interested in, otherwise, instead of throwing a die, you toss a coin. If you're interested in Boolean output.
Yeah, but like it could also be we're looking for a fix. Like
oh, yeah. But again, you have 2 possible outcomes: 6 or not 6. To be or not to be. To be 6 or not to be 6. Today I feel amletic, so sorry. Now, assume that you have a random source of bits, and the probability of generating a 0 is 2/3, and even a 1 is 1/3. Is this a Bernoulli trial? So every time you generate a bit, you have an oracle, you say, give me a bit. Out comes a bit. It's a 0 with probably 2/3, a 1 with probably 1/3. Then you say, oracle, give me another bit. Another bit comes out. And the bit goes on. Well, okay, and on and on. Well, how many outcomes do you have? 2. The probability of success, assuming that 0 means success and 1 failure, the probability of success is 2/3. The probability of failure is 1/3. Now, are these Bernoulli trials mutually independent? I told you the source of bits is random, so you can assume that they are. So every time you get one or the other with a given probability. If this was a deterministic generation of bits, then perhaps it would not be mutually independent. Perhaps the generation of the next bit depends on some history of what has been generated so far, or parts of it. We don't know. But if it's completely random, then it's a mutually independent Bernoulli trial. So if I ask you, what is the probability of obtaining exactly 3 ones out of 5 randomly generated bits? What would your answer be? Scratch pad. Okay, so the probability of 0 was 2/3. The probability of a 1 was 1/3. And now I ask you, what is the probability of getting 3 exactly 3 ones out of 5 bits? What is this probability? Okay, yes. So we want to find out how many possible ways do I have to put exactly 3 ones in 5 slots, which are the 5 bits. So this should ring a bell. I need to choose 3 slots for the ones out of 5. Does this smell like something you know? Or something that you should know? or something that you used to know. That's even better. Thank you. Does it smell like the binomial coefficient? 5, choose 3. Choose 3 possible places where to put the ones out of 5. And what is this? This is 5 factorial divided by 3 factorial times 2 factorial. Which is what? It's 5 times 4 divided by 2. So that should be 10, unless I'm mistaken. So there are 10 possible bit strings that have exactly 3 ones. Okay, so what is the probability that a bit string of length 5 has 3 ones? Well, you know that these are all mutually independent. You know what is the probability of getting 1, 0. You know what is the probability of getting 1, 3. So the probability of getting 3 ones is 1/3 to the 3rd times the probability of getting, if you get only exactly 3 ones, you get 2 zeros. So that's 2/3 to the square. That's the probability of getting 3 ones. That's the probability of getting 2 zeros. But that's the probability of getting 1 bit string with 3 zeros and 2 ones. Sorry, with 3 ones and 2 zeros. Well, there are 10 of them. So you need to multiply this by 10. Okay, so what we just used is the formula. This is not it. It's the formula for calculating the probability of k successes in a sequence of n Bernoulli trials. The probability of getting k successes, in our case it was 3 ones, in a Bernoulli trial consisting of n events in a sequence, is all the possible numbers of way of choosing the k successes out of n. So it's n choose k. And then the probability of getting the k successes, which is p to the k, because p is the probability of success, and the probability of getting failure, namely 1 over p, in all of the remaining time cases, the n minus k cases. So this is an example of a Bernoulli probability distribution. So for instance, if somebody gives you a fair coin and you want to know, okay, so what is the probability that I get out of 10 coin flips, I get 3 heads? Well, you use this formula. And this works even for an unfair coin, where P is different from Q. The only thing is that sort of the binomial coefficient tells you how many possibilities you have of generating the outcome that you're interested in. Next week, we are going to start by having a look at an application of binomial distributions and Bernoulli distribution and of this formula here to figure out what is the probability that you can successfully transmit a bit string, assuming that your transmission is based on a coding that can correct a certain number of errors. That's again a Bernoulli trial, and this formula actually tells us how to calculate the probability of a successful transmission. That would be a motivating example. Any questions before we break? Well, break metaphorically and not physically. Okay, anyway, you know you're always welcome to ask questions at any point. And with this commercial message, I'm going to go offline.